Okay, so it's 12:30 today. We have a lab scheduled for today. I just remembered to actually pass out the sheets to this group of students, which I forgot to do the last time we did this. On the sheet, it says that the lab will take 60 to 80 minutes. That is wildly untrue. If I'm doing it for you, it'll take 20 tops. So I guess that begs the question, do you guys want to spend 20 minutes or so reviewing anything before we jump into the lab, or you just want to get out of here early because it's a Friday afternoon? Second one. Okay. Resoundingly the second one. Okay. So let's look at the lab assignment sheet then real quick. If I can find it. Here we go. So this is a lab assignment on utilizing operational amplifiers. I am going to kind of lecture just a small amount during the middle of this thing to talk about some things. One thing that I'd like to point out, the only thing that we're really using in this is a 1 kilo ohm resistor, a 2 kilo ohm resistor. Oh, I should show this stuff to everybody who's in the room too. And now my laptop is making 14 different noises. Come on, there we go. All right. So we're going to use a 1 kilo ohm resistor, a 2 kilo ohm resistor, and this TCA 0372 op-amp integrated circuit. This is all kind of stuff about the Digilant board that you don't need to worry about because I'm handling it all. So our first step here is use a multimeter and measure our two resistances. So my first resistor has a value of 0.987 kilo ohms, so 987 ohms. Put this guy back in the circuit where it's supposed to go. And my second resistor, that's just my wife, has a value of 1.96 kilo ohms. Come grab a sheet up here, please. 1.96 kilo ohms. Let me put this guy back in. All right, so I think we're done with our multimeter part. That in 1.96 kilo ohms. All right, so a physical op-amp, here's a picture one, looks vastly different than what we would see. It's not triangular in any way, shape, or form, just because that would be, it wouldn't fit well on breadboards and all that kind of good stuff. Some older op-amps are actually made out of like a little cylindrical canister with 8 pins sticking out, so it kind of looks like a spider. But this is a much more common configuration now, where this is called like a dip chip because it's dual inline pins. There is a notch on the op-amp that tells you, why is it making so many weird noises? That tells you where pin 1 is. So if you can see, and maybe this drawing is pretty crappy, but as you can see right here, there's that notch, and then there might also be a little dot there. Well, the pin to the left of the notch, this is pin 1, then 2, 3, 4, and on the other side it wraps around 5, 6, 7, and 8. So that's how the pins are labeled on a dual inline pin chip like this. The particular op-amp that we're using doesn't actually have, so each op-amp itself contains 3 pins, our inverting input pin, our non-inverting input pin, and an output pin. So those are 3 pins. There are 2 op-amps on our chip, so that makes 6 pins. And then there's the positive power supply voltage pin and the negative power supply voltage pin. So this particular chip doesn't actually contain any pins for us to do any correction. So in a real op-amp, it's actually pretty common to see that if you have a 0 voltage differential input signal, meaning if you grounded pins 7 and 8, you might see a small voltage at pin 1 here, and it would contain pins in order to offset that. This is a cheap chip because everything we buy here at Tech is cheap. It does not contain those special features. So all we have access to are our inverting input, our non-inverting input, power supply, and the outputs. All right. So for this lab, we are going to be making a non-inverting amplifier circuit, which I've already constructed. And tells us that the amplifying circuit above behaves according to this equation. So this is where I'm going to lecture a very, very small amount, okay? We're told in the next statement that we want a gain of approximately 3. If we look at this circuit and we know that it has this behavior, and let me zoom out so we can maybe see both at the same time. So we have this circuit with this particular input-output relationship. Is the 2 kilo ohm resistor supposed to be our feedback resistor, or is the 1 kilo ohm resistor? Feedback resistor is the one labeled RF. The 2 kilo ohm resistor has to be the feedback resistor. Absolutely right. So if we put the 1 kilo ohm resistor in the feedback position, then we would have a gain of 1.5, because 1 plus 1 over 2 is 1.5. So in order to hit our gain of 3, we need to put the 2 kilo ohm resistor in the feedback position and the 1 kilo ohm resistor at the input position. If you guys were doing this, you would be amazed at how many questions I get about which resistor goes where and blah, blah, blah. The equation tells you exactly what to do, right? There's a well-defined input-output relationship here. All right, so this tells you how to build it. We've already done all of that junk. So now it's onto this page where we're going to measure the values for the peak-to-peak value for the input voltage and the output voltage. So let me switch over to the waveforms app. Communication has failed. Okay. So let me start this. So those of you who are on Zoom, what screen are you seeing right now? So I'm not confusing myself.
Waveforms.
Great, thank you. All right, I'm gonna need to move this a little bit out of the way. So right now everything is off. So I'm gonna turn on the WaveGen and I'm gonna turn on the scope, and I get this ugly looking thing, okay? The reason why I'm getting this very ugly looking output here, so the yellow curve is our input signal. It is a 2 volt peak to peak sinusoidal wave. And we would expect for an op-amp that our output, if we have a gain of 3, we should see the blue curve is just 3 times as large as the yellow curve. The reason we are not seeing that is because op-amps are active devices. So as soon as I press this play button here to turn on my power supply, we see that our signal jumps up. That's also a very, very common mistake I see students make. They forget to actually connect the power supply to the op-amp. It does not work if you don't give it power. So hopefully it should be fairly obvious to everybody that we have successfully created a non-inverting op-amp here, because we can see that the blue signal is 3 times as large as the yellow signal. Everything is perfectly in phase. We don't have to worry about anything like that. But we can see that if the yellow signal is, its peak is at 1 voltage division above our horizontal axis, while the blue curve, its peak is at 3 voltage divisions above the horizontal axis. So we have a gain of 3 over 1. So what's our peak to peak voltage for our input signal, which is the yellow curve? So what's the value at the positive peak? What's the value at the negative peak? So what's the peak to peak voltage? 1 minus -1 is 2. All right, so what's the peak to peak voltage for the output? 6. There we go. So that's what you put in your little table there. So V in should be 2 volts, V out should be 6 volts. Calculate the actual gain of the op-amp using the V in and V out calculated above. Well, that's pretty easy. 6 divided by 2 is simply 3. Then it asks you to calculate the theoretical gain of the op-amp, assuming it's ideal, using the measured resistor values. So that is 1 plus 1.96 divided by 986, I think. Oops. 1 plus 1.96 divided by 0.986, because I got my units messed up there. 2.987 and some change, so really, really close to 3. So our practical op-amp circuit behaves extremely close to what we would expect an ideal op-amp circuit to behave like. For the second part of the lab, we're told to make a non-inverting amplifier circuit. And so I want to draw both the inverting op-amp and the non-inverting op-amp circuits right next to each other so we can talk about the differences here. Let's see. The screen correctly. There we go. So for our non-inverting op-amp circuit, we had this. Here's V in. Here's our feedback resistor RF. Here's our output voltage V out. And then here's our input resistance Rn. So over here we have a non-inverting op-amp. Now we are constructing an inverting op-amp. So we have our feedback resistor RF. Here's Rn. And here's Vn. So what's the difference between these two circuits? So literally all that we've done to get from the circuit on the left-hand side to the circuit on the right-hand side is swap where we apply V in and ground. That's literally it, right? So if we moved V in over to the left-hand terminal of Rn and put ground at our non-inverting input terminal, we would have exactly this circuit. Let's see what chat's saying. Yep, so Cade nailed it. That is literally the only difference between these two. So if we jump back over to waveforms, and I tell the device to connect again, if I can see it, it's not detecting it, so something is loose. All right, run, run, run. Go back to my scope tab. I'm literally going to change 2 wires. And we now have our inverting op-amp. That's literally all it takes. That's another place where students typically tend to struggle when they do the labs themselves. They will break down the whole circuit and try to redo it, when you can literally look at our schematic diagram and realize that if you switch where you apply the input to where ground was and vice versa, you have your new circuit. So this is a inverting op-amp because when our input signal goes low or is negative, our output signal is positive and vice versa. Over here on the right-hand side, when our input signal is positive, our output signal is negative. Our gain is now obviously different because we can see that when our input signal is 1 division above the horizontal axis, our output signal is 2 divisions below the horizontal axis. So if we go to page, the bottom of page 6, what is the peak-to-peak voltage for our input signal, which is the yellow curve? Still 2, we didn't change anything. What is the peak-to-peak value of the output signal? 4, right? Nothing hard here. And so therefore our voltage gain, V out over V in, is what? 2. So the theoretical gain of the op-amp should be negative 1.96 divided by 0.986 is negative 1.987, blah, blah, blah. And our very last question says that the peak-to-peak voltage of V in and V out are both positive. So where did the negative sign on our gain go when we measured it that way? Anybody got any thoughts? So our theoretical gain is -2, and our measured gain is +2. What fundamental mistake have we made? Let me ask you a slightly different question then. Is it humanly possible to get a negative peak-to-peak value? No. That's where the negative sign went, right? It's not taking into account the phase difference between these 2 signals. We can obviously see that when the input signal is negative, the output signal is positive, et cetera. When you do a peak-to-peak value, it's literally positive peak minus negative peak. It can never give you a negative value. So that's where the negative sign went. Okay, so that's a lab in 20 minutes. Yes, ma'am. The theoretical gain of the first circuit, 2.988 volts per volt. 1 plus 1.96 divided by, wait, maybe I missed. Yeah, divided by 0.986 or something like that. Whatever our measured resistor values were at the beginning. And then the same thing for the theoretical gain of the second one. You just put in the 1.96 for RF because that's our feedback resistor, and 0.986 or whatever for R1 because that's our not feedback resistor. All right, so let's see what's popping in the chat. Cade, the voltage gain value is positive only when we're measuring peak to peak. And it's because we can't get a negative value for peak to peak. The voltage gain should be -2 volts. And it's because we see that for a positive input signal, we get a negative output voltage and vice versa. So unless anybody has anything else they want to talk about, catch you guys on Monday for the review session will be on Zoom. just so everybody can join at the same time, so I don't have to answer the same questions more than once. And then test is at 6 upstairs here. So yes, turn that in over here on this side of my desk, please. It's positive for the one that's V out over V in because we measured V out as a peak-to-peak voltage and V in as a peak-to-peak voltage. If we measured V out and V in as a peak to the horizontal axis, so yeah. Okay. Alrighty. Catch you later. You too.
Have a good weekend.
You too. Alrighty, you cats on Zoom. Is it all right if I stop sharing the screen and all that kind of stuff since we've wrapped up? It's Friday. So it's 1:30, so it's time to get started. If you look at the lab sheet that I've just passed out, and I'll bring it up for those students on Zoom. I also need to let's see, I have 4,000 windows open. This is the one I'm looking for. All right, so as I was saying, if you look at this lab sheet up at the top, it says that it will take 60 to 80 minutes. That's probably true if you guys were doing it, but with me doing it, it's gonna take like 20 tops. So with that in mind, we're gonna have some extra time today. So we could spend that time doing some review, or we can leave early because it's Friday. What is your preference? You might want to review some stuff, that's fine. Okay, so you want to okay. So you don't want me to look at one of those transient analysis problems? Sure, okay.
I think something we can also do is like review the formulas we need to remember, like say power or energy equals count of. Sure.
So let's do the equations first because I can knock all those out pretty quickly. So my expectation for the equations that you should know. So let's write inductors over here. I'm going to draw a picture of one. Let's define this voltage as VL, the voltage drop over the inductor. Here is the current IL flowing into the inductor, and the inductor has a value of L. And then over here on the other side, these are our relationships for capacitors. And I'll draw a picture of a capacitor. C. And then we have the voltage drop over a capacitor as a function of time, and the current flowing into the capacitor as a function of time. Come grab one of these sheets if you wouldn't mind, miss. Doing a very brief review before we jump into the lab here. So for the inductors, we'll start with our fundamental relationship. That is the voltage drop over an inductor is equal to the inductor value multiplied by the derivative of the inductor current with respect to time. Okay, so that's our first equation for inductors. We can use the concept of duality, noting that the capacitor is the electrical dual of the inductor, to then get the equation, or well, this will be number one for capacitors. So when things are an electrical dual, I can replace all my V's with I's and all my L's with C's and vice versa. And so I'll find that IC of T is equal to C dV by dt. These expressions are identical, except we've replaced voltage with current and inductance with capacitance. Our second equation for each case comes from multiplying both sides by dt and then taking the derivative, and then performing the integration. And so we'll find that IL of t is equal to 1 over L, the integral from some point in time where the current is known to some later point in time of the inductor voltage with respect to x, where x is just a dummy variable representing time, plus our initial condition on the inductor current. And so our integral relationship for capacitors is then Vc is equal to 1 over C, the integral from T naught to T of IC of X with respect to X plus Vc at T naught. Our third equations will be regarding power. Fundamentally, the power absorbed by an inductor is simply the current flowing through the inductor multiplied by the voltage drop across the inductor. But we can also write this by substituting equation 1 in. We'll see that this gives us L I di by dt. And for our capacitor, we have the fundamental relationship I times V, which can be rewritten, substituting equation 1 in again, as C V dV by dt. And then lastly, if we were to integrate equation 3, where the limits of our integration are negative infinity, where we're assuming that at negative infinity, our element does not have any stored charge or stored current, we get WL of T, the energy stored by an inductor, is 1/2 L times the inductor current squared. And similarly, for a capacitor, the energy stored is 1/2 C times the square of the voltage. So those are the 8 equations that I'm expecting you to know. And if you know 4 of them and you recognize that they're electrical duals, you know the other ones. It's literally just replacing I with V and L with C and vice versa.
And
L is the value of the inductors measured in henries. C is the value of the capacitor measured in farads.
I think that's something that kind of gets me off guard each time, remembering that L means inductor, because you already have I in current.
Right. Yeah. No problem. All right. So there was also right. So there was also asking me to work a problem, one of the transient analysis problems from an exam. So let's find an old exam. Do you care which exam I work it from? All right. So let's just do exam 2, summer. And I think we'll jump down to problem 25-ish. It's 26. All right. So in this circuit, the switch has been open for a very long time before closing at t is equal to 0. This one actually might be too easy, but we'll still work with it. So number 26 tells us that we want to determine the value of the inductor current at t is equal to 0 minus. Well, in this case, if this switch is opened, then this guy right here is an open circuit, right? Which means there's no independent sources connected to the inductor. So it should be fairly easy to see that the answer is 0 by inspection. No need to do any extra work. Anybody have any questions or comments about that? Right. For part 2, it wants us to find the voltage at t is equal to 0 plus. So at t is equal to 0 plus, our switch looks like a short circuit, and our inductor is going to behave like an open circuit because we know that exactly 0 amps of current flows through it. So our voltage here, V of t, I'm going to find by using current division and then Ohm's law. Is there enough space down here? Sure. So I have, so let's see, V of t is going to be equal to negative 10 milliamps. I'll explain where that negative sign comes from in a second. So I'm going to have 1 over 3 kilo ohms plus 2 kilo ohms, right? So I have this branch, and this branch that I'm looking at. So I'm trying to find the current through that rightmost branch, again, treating the inductor as if it were an open circuit. So that means I'm going to have 1 over 3 plus 2 divided by 1 over 5 plus 1 over 6 plus 1 over 3 plus 2, where I'm ignoring the units because they're all going to cancel each other out anyway. And then I'm going to multiply that by 3 kilo ohms. And that's going to give me my voltage drop. Come grab one of these sheets, Chief. The negative sign comes from the fact that the current is flowing into the negative polarity terminal, right? Our voltage V is defined positive polarity on the right, negative polarity on the left. And I can see that my current, using current division, tells me that the current's flowing into the negative polarity terminal. So that's where this negative sign comes from. So put that in, negative 10 times 3 times 1/5 over 2/5 plus 1/6, negative 180 over 17, or negative 10.588. 23529 ... if you want to. So any questions about how I used a combination of current division and Ohm's law to get that voltage drop? You could have also done nodal analysis or mesh analysis or anything else. That's just my lazy way of getting it in one step. For part, so number 28, we want to find what's going on at t is equal to infinity. So at t is equal to infinity, our inductor is going to look like a short circuit, which means this 2 kilo ohm resistor doesn't contribute anything. So we're going to do the exact same thing. We're not going to, well, I was going to say we can use voltage division and then Ohm's law, but that's going to look the exact same thing as just finding the equivalent resistance of all 3 of these resistors and then multiplying it by that 10 milliamp source. So you can use Ohm's law, or you can use, find the equivalent resistance and use Ohm's law, or do current division and then use Ohm's law, and the equations will look literally identical. So V at infinity is going to be negative times 10 milliamps times one over 5 plus 1 over 6 plus 1 over 3. The 2 kilo ohm resistor is shorted out, so it's not contributing. Yeah, I'm just double checking. I definitely make mistakes.
Oh, yeah, I got it already.
Yeah. Negative 100 over 7, which, yeah, negative 14.286. Volts, or 285.71429, etc. So now we know how it's behaving at t is equal to 0 minus, t is equal to 0 plus, t is equal to infinity. So the next thing we need is the time constant. So the time constant is during the transient condition. So that means this guy is closed. We're taking our inductor out and looking in. And we're looking at a dead network. So this guy is off. So let me redraw this down here. If I'm not mistaken, this is what our circuit looks like, 5 in parallel with 6. Yep, all right. So on the left-hand side, we have 5 times 6 over 5 plus 6 plus 3. .143 kilo ohms. On the right-hand side, we have 2 kilo ohms, and these guys are in parallel. So Req is RL times RR over RL plus RR. .30 over 29, 1.0344 and some change kilo ohms. Obviously, our equivalent inductance is 25 millihenries. And tau, that does not look like a tau, is LEQ over REQ. So that's 25 times 10 to the minus 3 divided by that. And I get 24.167 milliseconds, which is not what I got up there. So what did I do wrong?
Oh, very good. Very good.
Oh, yeah, I made a fundamental mistake on the left-hand side because obviously the answer should be greater than 3 if I'm adding 3 to it. So there's something, I did something dumb there. So let's see, 5 times 6, so 30 over 11 plus 3, 63 over 11, 5.727 kilo ohms. Yeah, in parallel with 2. So that's x plus 2 over, no, x times 2 over x plus 2. 1.482 kilo ohms. 25 times 10 to the minus 3 divided by, yeah, so that was lab. 16.865 microseconds, which is what we get here. So yeah, I made a silly mistake there and didn't realize that it literally would have been impossible for the left-hand side resistance to be less than 3. So I obviously did something wrong in my calculator. So at this point, we know that V of t is going to be equal to, let's see, negative 10.588 minus negative 14 point something 286 e to the minus t divided by 16.865 microseconds minus, or let's just do plus negative 14.286 volts, and then we plug in our value for t. So yeah, on the exam, it'll be just like that, step by step. Analyze the circuit at t is equal to 0 minus, analyze it at t is equal to 0 plus, analyze it at infinity, calculate the time constant, plug everything together to our generic expression. The generic expression is, oh, and this is only valid for t greater than or equal to 0 plus. Y at 0 minus, for t less than 0 minus, y at 0 plus, minus y at infinity, e to the minus t over tau, plus y at infinity for t greater than or equal to 0 plus. So that's the generic expression, regardless of if it is a RC circuit or an RL circuit. You can use this whether it's a total response problem or a natural response problem. In a natural response problem, this guy just goes to 0, and this guy just goes to 0, which would match the original equation that we gave you guys. So exactly right. For any RC or RL, so any first order transient analysis circuit, this is how it's going to behave. All right, any other review type questions, or can we jump into the lab? All right, let's go with the lab. So circling back over here, I want you guys to recognize we're only using 3 components in this lab: a 1 kilo ohm resistor, a 2 kilo ohm resistor, and this TCA 0372 op-amp. So the first step is to measure both resistors. I did that previously, and so our 1 kilo ohm resistor has a value of 986 ohms, and our 2 kilo ohm resistor has a value of 1.96 kilo ohms. And then we have a picture of a TCA 0372 op-amp. So it may be, wait, am I sharing? Yeah, I've been sharing that screen the whole time. Okay. So it tells us to notice that there is a curved notch, which is kind of hard to see in this black and white photo. But if you look at the op-amp in your kit, it's either going to have that curved notch at one end, or it's going to have a little indentation here. And to the left of that notch is pin 1. Then we count off 2, 3, 4, and on the other side would be 5, 6, 7, and 8, like so. This is what's known as a DIP chip, DIP for dual inline pins, or I think it's actually dual inline pitch, but it's just telling us that the pins are in a line on both sides of the chip. The other option for an op-amp, for an integrated circuit op-amp like this, would be a small metal canister with 8 legs sticking out that looks kind of like a spider. But it's been a hot minute since those were produced regularly. Pretty much everything uses a dip chip configuration nowadays. The particular op-amp chip that we are using is actually 2 op-amp circuits on a single chip. So we only have access to the inverting and non-inverting terminals and the output terminals for 2 op-amps, as well as our power supply pins, which are labeled here. VP plus is for our positive power supply, and VP minus is for our negative power supply. If you went to, say, Mauser or DigiKey or something like that, the overwhelming majority of op-amp chips that you could buy would have a single op-amp on the chip, and it would still have 8 pins. So what's missing from this particular op-amp chip are means by which to correct for what's called a DC offset voltage. And so what that means is that it's fairly regular that if you apply, like if we grounded pin 8 and pin 7 and looked at the output, we might see that the voltage here, V out, is not equal to 0 volts. It'll have some small, typically on the millivolt scale, value, and those pins that are missing would allow us to bias that to get that output voltage to be 0 when we put an exactly 0 input in. But for whatever reason, we decided to go with this chip, which has 2 op-amps on it, and we only use one of them. Couldn't tell you why. All right. So this is our first circuit. We are making a non-inverting amplifier. If you watch the lecture video on my common amplifier topologies, this should look very familiar. And this amplifying circuit behaves according to this input-output relationship. We are trying to find, or trying to set up a circuit where it has a gain of 3, which means that V out divided by Vin, which is equal to 1 plus RF over R1 in our figure, must equal 3. So the question that I get asked a whole heck of a lot when the students do this particular lab experiment is which resistor goes where? And it should be extraordinarily obvious because of this equation, right? This guy right here is governing our output response. So if I want a gain of 3, is RF the 2 kilo ohm resistor or the 1 kilo ohm resistor? It has to be the 2 kilo ohm resistor, right? Because if our gain is 1 plus RF over R1, well, 1 plus 2 is equal to 3, and 1 plus 1/2 sure as heck isn't. So that tells us the feedback resistor here needs to be the 2 kilo ohm. You would be amazed at how many students can't figure that out. So I have gone ahead, this is a picture of how it's set up, but I have gone ahead and set it up, except that I haven't, so let me fix it. I have the wrong circuit up. All these are just steps on how to set everything up. I've already done that. So let's take a look at our waveforms. Communication has failed. So incredibly loud. Now board power is off. Now it's on. Let's move this out of the way. So I have a wave generator here. We've been told that we need to generate a 2 volt peak to peak waveform. So that's why it's set for an amplitude of 1. So it's 1 volt above and 1 volt below gives us 2 volts peak to peak. I've turned that on. And now I'm turning on my scope and I see the hottest of garbage. Okay. The yellow curve is our input voltage and the blue curve is our output voltage. If we have a gain of 3, our expectation is something like this. I'll do this whiteboard thing. So we have an input signal like so. How do I change the colors? This is what happens. Format, no. So our expectation is for an input signal like this, purely sinusoidal, where this is 1 volt and this is -1 volt, that our output should be something like this, where this is 3 volts and this peak is at -3 volts. And that's absolutely not what we are seeing. The reason we aren't seeing that is because this op-amp is what's called an active device, meaning it requires external power, and I never turn the external power supplies on. Now, as soon as I do that, we get the exact response we're expecting. So when my voltage signal is at +1 volts, my output is at +3 volts. When my voltage signal is at -1 volts, my output is at -3 volts. That's why this is a non-inverting amplifier. It just takes the input signal and scales it up by a particular factor based on that ratio of resistances. I don't know what all that crap said. So if we go back to our sheet thing, looking at the bottom of page 5, it asks us to determine the peak-to-peak values for the input signal, which is the yellow curve, and the output signal, which is the blue curve. So what's the peak-to-peak value for the yellow curve? 2 volts peak-to-peak. What's the peak-to-peak value for the output, the blue curve? 6, all right? So Vn should be 2 volts peak-to-peak, Vout should be 6 volts peak-to-peak. The next step asks us to calculate the actual gain of the op-amp using the values of Vin and Vout. What's that going to be? 3, absolutely right. And then the next step asks us to calculate the theoretical gain of the op-amp using the measured resistor values. So go ahead and take a moment to do that and tell me what your answer is. Three points after the decimal. Sure, sounds good. Really close to 3 should be what the answer is. We can see that our practical op-amp circuit is behaving extraordinarily similarly to what we would expect of an ideal op-amp circuit. That's one of the really great things about practical op-amps, is that while they do have a finite input resistance, a finite open loop gain, and a finite output resistance, they still behave very, very close to an ideal operational amplifier. All right, so now that we've calculated the theoretical gain of our op-amp, our next step is to change our circuit, where we're told on the top of page 6 to create a non-inverting amplifier circuit. So I want to look back at my notes here real quick. Let's go back to page 1. So on the left-hand side, I have drawn a non-inverting op-amp. And on the right-hand side, I have drawn a picture of an inverting op-amp, or at least their schematic diagrams. What's the difference? Right, so really all we're doing to convert our circuit from the non-inverting op-amp to the inverting op-amp is we are changing the pin where we're applying our input voltage and moving it over here to that other leg of the resistor. And then we're moving ground from that leg of the resistor to the input. That's literally the only difference. So we have our op-amp, and I am going to change 2 wires. And we now have an inverting op-amp. I literally just changed the wires that corresponded to our input voltage and our ground. So this is an inverting op-amp because we can see that when the voltage has, the input voltage is negative, our output voltage is positive. When our input voltage is positive, our output voltage is negative. So we can say that these two signals are 180 degrees out of phase, or they're scaled by a factor of -1 times some number. So what is the peak-to-peak value for our input? The yellow curve. Still 2. We didn't change it at all. What's the peak-to-peak value for our output curve? 4. So calculate the voltage gain. 4 over 2 is 2, right? Now, the theoretical gain of the inverting op-amp circuit is negative RF over R1. So use your resistor values and calculate that for me real quick. -1.96 over, or excuse me, negative 1.96 over 0.986, I think. Negative 1.98, 1.99, something like that. Okay, so the very last bullet point here says the peak-to-peak voltage of Vin and Vout are both positive. So where did the negative sign go? Effectively, it's asking, why is there a discrepancy between the voltage gain calculated with the theoretical and the voltage gain calculated using peak-to-peak values? Because AV with peak-to-peak values gave you +2, and AV with the theoretical expression gave you -2. Where did the negative sign go? Let me ask a slightly different question. Is it possible to get a negative number for a peak-to-peak voltage? Yeah, that's where the negative sign went, right? So measuring the voltage gain using only peak-to-peak values is throwing away the fact that these two signals are out of phase, right? So we can see, based on our experimental data, that when the input voltage is negative, the output voltage is positive and scaled by a factor of 2, so that there is a gain of -2. And likewise, on the right-hand side over here, when our input voltage is +1, our output voltage is -2. So -2 divided by +1 still gives us a gain of -2. So that's just, I guess, a little bit of a warning. When you're actually calculating the gain, use the value of the input voltage that corresponds to the value of the output voltage. Don't use peak-to-peak, because it's very easy to make a simple mistake like that. And that is the lab. So any questions or anything like that? Technically, it has units of volts per volt. Well, voltage gain has units of volts per volt, but volt per volt cancels out, so it doesn't particularly matter. But if you looked at a spec sheet for an operational amplifier or something like that, it would typically tell you what the gain is in volts per volt. All right, so unless anybody has any questions or anything, that is it for today. Please turn in your assignment over here on the right-hand side. I'll put on my mask.
What is the principle of current doesn't immediately change?
Inductors. The current through an inductor cannot change abruptly. The voltage drop over a capacitor cannot change abruptly. Those are the only two quantities that we have discussed that cannot change abruptly.
Okay.
Thank you, ma'am.